Picture a universe where everything you know has an identical twin, same mass, same energy, but with one crucial difference, an opposite charge. This isn't science fiction. It's the real, mind-bending reality of antimatter, nature's perfect mirror to the matter that makes up our world. And yet, here's the cosmic puzzle. If matter and antimatter were created in equal amounts during the Big Bang, why does our universe today seem to be made almost entirely of matter? Where did all the antimatter go? This isn't just a quirky detail, it's one of the greatest unsolved mysteries in physics, a question that challenges our very understanding of existence. Without this imbalance, stars, planets, and even you wouldn't be here. So what happened to tip the scales? Think of it like a cosmic magic trick. When matter and antimatter meet, they annihilate each other in a flash of pure energy. In a perfectly symmetrical universe that should have left nothing behind, just an empty void. Yet here we are, surrounded by galaxies, planets, and life itself. Scientists call this the matter-antimatter asymmetry, and solving it could rewrite the laws of physics. Imagine holding two coins, one ordinary, one made of antimatter. Flip them and they should always land the same way, but somehow the universe flipped them unevenly, leaving us with a surplus of matter. How? The answer might lie in hidden flaws in the fabric of reality itself, tiny cracks in the symmetry that governs everything from atoms to galaxies. This isn't just about abstract physics, it's a story about how our universe came to exist at all. Every atom in your body, every star in the sky, exists because of this mysterious imbalance. And the hunt for answers has led scientists to some of the most extreme places in existence, from the searing heat of the early cosmos to the depths of underground particle colliders, where we recreate conditions a fraction of a second after the Big Bang. Along the way, we've uncovered clues that defy expectations, like antimatter particles that don't behave exactly like their matter counterparts. Could these subtle differences hold the key? Strap in, because we're about to dive into one of the most profound questions science has ever asked. Why is there something instead of nothing? To understand why our universe favors matter, we first need to grasp the strange nature of its shadowy twin. Antimatter isn't some exotic substance from a sci-fi movie. It's a fundamental part of nature, perfectly mirroring ordinary matter in almost every way. Take an electron, for example, tiny, negatively charged and whirling around atoms. Its antimatter counterpart, the positron, has the exact same mass but flips the script with a positive charge. The same goes for protons and antiprotons, nearly identical yet opposites in charge. Even neutral particles like neutrons have antineutrons, where subtle quantum properties are inverted. These aren't just theoretical curiosities, we've actually created and studied them. When antimatter meets matter, the result is pure energy, a flash of gamma rays as both particles vanish. This mirror-world behavior isn't just confined to labs. Antimatter plays a surprisingly practical role in modern life. Hospitals use positrons every day in PT scans, where doctors track these antimatter particles to map out everything from brain activity to cancerous tumors. The positrons annihilate with electrons in your body, releasing energy that machines detect, painting a detailed picture of what's happening inside you. It's a brilliant example of how quantum oddities can save lives. Yet for all its similarities, antimatter holds mysteries that keep physicists awake at night. According to Einstein's equations, the Big Bang should have produced matter and antimatter in perfect balance. So why didn't they wipe each other out completely? The fact that we're here at all suggests something tipped the scales. Some hidden asymmetry in the laws of physics that allowed matter to dominate. Maybe antimatter behaves slightly differently under certain conditions, or perhaps there's an entire shadow universe of antimatter galaxies we've yet to discover. Whatever the answer, unraveling this cosmic riddle could rewrite our understanding of reality itself. The story of antimatter begins not in a high-tech lab but on paper, with a young physicist named Paul Dirac wrestling with a mathematical paradox in 1928. His equations describing the behavior of electrons kept breaking down unless he accounted for particles with identical mass but opposite charge. At first, Dirac assumed this was just a quirk of the math, but the universe had other plans. What he'd stumbled upon was the first theoretical evidence that for every particle, a mirror image must exist. The scientific community dismissed it as a curiosity, until nature itself proved Dirac right in the most dramatic way possible. 4 years later, Carl Anderson was studying cosmic rays high-energy particles from space when his cloud chamber captured something impossible, a particle with the mass of an electron but curving the wrong way in a magnetic field. It wasn't an electron at all. It was its antimatter twin, the positron, dancing through Anderson's detector like a cosmic whisper. The moment he confirmed its existence, physics changed forever. Imagine the thrill of discovering an entire shadow world hiding in plain sight, a revelation so profound it earned Anderson the Nobel Prize by 1936. But here's what makes this discovery even wilder. Anderson wasn't looking for antimatter. Like so many breakthroughs in science, it came by accident, hidden in the static of cosmic rays bombarding Earth. Picture him in that Caltech lab, staring at trails of condensation left by particles zipping through his chamber, when suddenly there it was, a single track curving the opposite direction of everything else, defying expectations. That tiny deviation was the first tangible proof that Dirac's equations weren't just elegant math. They were a roadmap to a hidden layer of reality. This wasn't just about adding a new particle to the textbooks. Anderson's discovery cracked open a door to deeper questions. If positrons existed, what about antiprotons, antineutrons? Could entire antimatter atoms form? Within decades, we'd find answers to all these, but the real shock was realizing how abundant antimatter should be. The cosmos clearly knew how to make it, so where did it all go? Dirac's equations suggested a universe perfectly balanced between matter and antimatter, yet Anderson's discovery hinted at a cosmos with a mysterious preference. That tension between symmetry in theory and asymmetry in reality is the pulse of one of physics' greatest mysteries, a trail that began with a scribbled equation and a curious streak in a cloud chamber. The idea of antimatter captures imaginations far beyond the lab. It's a staple of science fiction where it powers starships, fuels doomsday devices, and unlocks realities beyond our own. Take Star Trek, for instance. The warp core of the USS Enterprise runs on matter-antimatter reactions, channeling the energy of annihilation to bend space and propel the crew at faster than light speeds. It's a brilliant plot device, but the reality, we're nowhere near harnessing antimatter as a practical energy source. Here's the catch: creating just 1 gram of antimatter would require the energy output of several nuclear power plants running for years, not to mention the challenge of storing it without touching ordinary matter. A single mishap would trigger an explosion dwarfing conventional bombs. Then there's Dan Brown's Angels and Demons, where a secret society threatens Vatican City with an antimatter bomb. The book paints a terrifying scenario, a tiny vial unleashing destruction comparable to Hiroshima. But the science behind it is stretched thin. In reality, the energy released from annihilating a gram of antimatter would indeed be massive, about 43 kilotons of TNT. But producing even that minuscule amount would cost billions and take decades with current technology. Fiction glosses over the colossal engineering hurdles, turning antimatter into a convenient shortcut for storytellers. Yet these exaggerations aren't just Hollywood fantasy, they reflect a deeper truth. Antimatter does hold incredible potential. NASA has studied it as a theoretical fuel for interstellar travel, where efficiency matters more than cost. A matter-antimatter engine could, in theory, accelerate a spacecraft to a fraction of light speed with minimal fuel mass. The catch: we'd need breakthroughs in containment and production that border on magic by today's standards. What's fascinating is how these portrayals shape public perception. Antimatter in pop culture often plays the role of a mysterious, volatile force, something between a miracle and a menace. Rarely do stories explore its quieter, real-world applications, like medical imaging or cutting-edge particle research. The gap between fiction and reality isn't just about creative license. It mirrors our own awe at a substance that embodies one of physics' greatest puzzles. Every warp drive and apocalyptic plotline taps into a genuine scientific mystery. Why does our universe cling to matter while antimatter lurks in the shadows? These stories, however fanciful, keep that question alive in the collective imagination, reminding us that some truths really are stranger than fiction. At the dawn of everything, mere fractions of a second after the Big Bang, our universe was an unimaginably dense, searing hot soup of energy. In those earliest moments, pure radiation constantly transformed into pairs of particles and antiparticles, flickering in and out of existence like cosmic fireflies. For every proton born, an antiproton emerged. Every electron was matched by a positron. This was physics at its most symmetrical, a perfect dance of creation where matter and antimatter should have existed in flawless balance. According to our best theories, the universe had no reason to favor one over the other. Yet here's the twist: if that symmetry had held, none of us would be here to wonder about it. Think of it like flipping a perfectly fair coin trillions upon trillions of times. Statistically, you'd expect roughly equal numbers of heads and tails. But the cosmic coin toss didn't play out that way. Instead, for every billion antimatter particles annihilated in those first moments, one single matter particle survived. That razor-thin margin, just 1 in a billion, made all the difference. It's the reason galaxies, planets, and life exist. But how? Why would nature break its own rules? Physicists call this puzzle the Barrian asymmetry problem, and it's one of the most glaring gaps in our understanding of the universe. The plot thickens when you consider just how tightly balanced matter and antimatter were in that primordial inferno. Experiments show their behavior is nearly identical, governed by the same fundamental forces. Gravity treats them the same. Electromagnetism merely flips their charges. Even the strong nuclear force, which glues atomic nuclei together, doesn't discriminate. Only the weak nuclear force, responsible for radioactive decay, hints at a possible crack in the symmetry. In certain rare particle interactions, matter and antimatter don't behave as perfect mirrors. Could this tiny imperfection be the key? Imagine baking two identical cakes, but one mysteriously rises higher than the other. You'd scour the recipe for discrepancies. Was the flour measured differently? Was the oven temperature uneven? That's precisely what scientists are doing with the universe's blueprint. The slightest deviation in how matter and antimatter interact could explain the imbalance. Some theories suggest conditions in the early cosmos, extreme temperatures, densities, or even undiscovered particles might have tipped the scales. Others propose that vast regions of antimatter still exist, hidden beyond our observable horizon. What's astonishing is how high the stakes were in those first moments. If the symmetry had been even slightly more perfect, say, one surviving matter particle in every trillion instead of every billion, the universe would have been too sparse for stars to form. Conversely, a slightly larger imbalance might have left space cluttered with too much matter, collapsing early into black holes. It's as if the cosmos threaded a needle, landing on an imbalance just precise enough to allow complexity to emerge. This isn't just a physics problem, it's a question about why anything exists at all. And the answer, if we ever find it, could reveal hidden layers of reality we've yet to imagine. When matter and antimatter collide, it's like striking a cosmic match. A burst of pure energy erupts as both particles vanish in an instant. Picture an electron zipping through space, minding its own business, until it meets its arch nemesis, a positron. The moment they touch, they cease to exist as matter, converting entirely into gamma rays, high-energy light that carries away their combined mass. This is Einstein's famous equation, E equals mc squared, in action. The energy released isn't just theoretical, it's staggering. Annihilate just 1 gram of matter with 1 gram of antimatter, and you'd unleash enough energy to power a city for hours. Scientists have actually seen this happen. In particle detectors, streaks of light mark the paths of particles, and when matter and antimatter meet, those streaks don't just cross, they terminate abruptly in a flash. It's as if two runners sprinting toward each other suddenly dissolve into sunlight. These aren't gentle goodbyes, they're the most efficient explosions nature allows. Every joule of energy locked in the particle's mass gets released, leaving no ash, no residue, just radiation. What makes annihilation so fascinating isn't just the violence of the process, but its precision. The particles must be exact opposites, an electron with a positron, a proton with an antiproton. Mismatches won't trigger total annihilation. Imagine trying to fit two puzzle pieces together, only a perfect pairing works. This specificity hints at why the early universe's imbalance is so puzzling. If matter and antimatter were truly identical in behavior, their annihilation should have left nothing behind. Yet here we are, proof that the scales tipped ever so slightly in matter's favor. The echoes of these collisions are everywhere. Medical CT scans rely on positrons annihilating inside your body to create detailed images. Even bananas, yes, bananas emit positrons from natural potassium decay, though they're far too sparse to trigger noticeable explosions. But the grandest annihilation events happen in space, where cosmic rays constantly rain down, occasionally meeting antimatter particles and vanishing in silent bursts of light we can detect across the galaxy. This process isn't just destruction, it's transformation. Energy from annihilation fuels some of the universe's most violent phenomena, like quasars and gamma-ray bursts. It's a reminder that matter isn't truly lost. It simply changes form, obeying the universe's unshakable ledger of energy conservation. Yet for all its power, annihilation leaves us with a haunting question. If matter and antimatter are so perfectly mirrored, why did the universe choose sides at all? The answer might lie not in the explosions themselves, but in the subtle cracks in the mirror we've only begun to glimpse. Deep in the quantum rulebook of the universe, there's a line that might have been crossed, an exception to nature's love of symmetry called CP violation. The C stands for charge, flipping a particle's positive to negative. The P is parity, swapping left for right like a mirror reflection. Put them together and you'd expect antimatter to behave exactly like matter in reverse. But sometimes, just sometimes, it doesn't. This tiny hiccup in the cosmic rulebook could explain why we exist. Picture a spinning top, zoom in close enough, and you'll notice it wobbles ever so slightly off-center. That's CP violation in action, a minuscule but crucial imperfection in how particles decay. In the 1960s, scientists studying exotic particles called kaons noticed something bizarre. When these particles decayed, their antimatter counterparts didn't follow the exact mirror image path. It was as if the universe had a hidden bias favoring one direction over another. That discovery earned James Cronin and Val Fitch a Nobel Prize and handed physicists their first concrete clue to the matter-antimatter mystery. Here's why it matters. If CP symmetry were perfect, matter and antimatter would cancel each other out completely. But this flaw in the mirror introduces a tiny imbalance, like a rigged coin toss where heads comes up one extra time in a billion flips. Over the universe's searing early moments, that slight preference could have allowed one extra matter particle to survive annihilation for every billion collisions. Multiply that across the entire cosmos and suddenly, the stars and galaxies we see aren't so improbable after all. Yet CP violation alone doesn't solve the puzzle. It's not nearly strong enough to account for the universe's overwhelming matter surplus. Current measurements show it contributes maybe 1 part in 10 billion to the imbalance. That's like trying to explain a mountain with a grain of sand. So where's the rest coming from? Some theories suggest undiscovered particles, like neutrinos, might amplify the effect. Others propose that conditions in the early universe, wildly different from anything we can recreate, magnified these subtle biases into the cosmic imbalance we see today. The hunt for answers has led physicists to extremes. Particle colliders like CERN LHC meticulously track the decay of particles and antiparticles, searching for discrepancies in their behavior. Experiments with neutrinos, ghostly particles that barely interact with matter, hint at even deeper violations of symmetry. Each anomaly, each tiny deviation from expectation, is a breadcrumb leading us closer to understanding why the universe tilted in matter's favor. What's thrilling is how CP violation ties into one of the great unanswered questions: what happened to all the antimatter? If it truly behaved differently, could pockets of it still linger in distant galaxies? Or did it all annihilate, leaving behind only this faint statistical echo of its existence? Every measurement, every collision in particle detectors is a step toward rewriting the story of our cosmic origins. We're not just observers of the universe, we're the remnants of a broken symmetry, living proof that perfection isn't always what it seems. In 1964, inside a nondescript lab at Brookhaven National Laboratory, two physicists stumbled upon something that shouldn't have been there: a crack in the universe's mirror. James Cronin and Val Fitch were studying kaons, exotic particles that flicker in and out of existence like quantum fireflies, when they noticed something bizarre. These particles weren't playing by the rules. When kaons decayed, their antimatter counterparts didn't follow the exact reverse path. It was as if the universe had whispered a secret. Symmetry wasn't as perfect as we'd thought. The numbers were staggeringly small, a mere 0.2% difference in decay rates between matter and antimatter kaons. But in science, the tiniest deviations often hold the biggest secrets. This was CP violation in the wild, the first experimental proof that nature's mirror had flaws. The discovery sent shockwaves through physics, earning Cronin and Fitch the Nobel Prize and handing cosmologists their first tangible clue to the matter-antimatter puzzle. Imagine baking two identical cakes only to watch one rise slightly higher. You'd tear apart the recipe to find the hidden variable. That's exactly what physicists did. Kaons might seem obscure, but their behavior is cosmic detective work. These particles are chameleons, oscillating between matter and antimatter states as they travel. Normally, this dance should be perfectly symmetrical, like a pendulum swinging left and right with equal force. But Cronin and Fitch's data showed the pendulum occasionally favored one side. The implications were monumental. If antimatter doesn't always mirror matter, even by a hair's breadth, it could explain how a surplus of matter survived the Big Bang's annihilation frenzy. Yet here's the catch: 0.2% isn't nearly enough to account for the universe's overwhelming matter dominance. It's like finding a single puzzle piece that suggests a bigger picture, but where's the rest? Some theories speculate that kaons are just the tip of the iceberg. Other particles, like neutrinos or hypothetical superheavy relics from the early universe, might exhibit even stronger CP violation under extreme conditions we can't yet replicate. What makes this discovery so thrilling isn't just the data, it's the audacity of the experiment itself. Cronin and Fitch weren't hunting for cosmic asymmetry, they were probing the fundamentals of particle behavior. Their breakthrough came from noticing a whisper in the noise, a statistical hiccup others might have dismissed. It's a reminder that science often advances not by chasing grand theories, but by staring hard at the details and asking, why doesn't this add up? Today, their work fuels cutting-edge experiments at facilities like CERN, where scientists collide particles at near light speeds, searching for CP violation in other exotic particles. Every anomaly, every tiny deviation from symmetry is a potential clue to why we exist. The kaon experiments of the 1960s didn't solve the mystery. They lit the first torch in a cavern we're still exploring. And somewhere in the darkness, the universe's biggest imbalance might finally reveal its origins. To explain why our universe is filled with matter rather than nothingness, scientists turn to baryogenesis, the cosmic process that tipped the scales in matter's favor. Imagine a vast factory at the dawn of time, producing particles with an assembly line that somehow malfunctioned, churning out just a few more matter widgets than antimatter counterparts. That's baryogenesis in a nutshell, the mechanism that transformed a perfectly symmetrical early universe into the lopsided cosmos we inhabit today. The blueprint for how this could happen comes from Soviet physicist Andrei Sakharov, who in 1967 outlined three crucial conditions needed to create matter's dominance. First, there had to be CP violation, that tiny hiccup in symmetry we see in particle decays, where antimatter doesn't quite mirror matter's behavior. Without this, the universe would have remained perfectly balanced, cancelling itself out into oblivion. But CP violation alone isn't enough. Sakharov's second condition requires baryon number violation, a break in the rule that the total number of protons and neutrons, collectively called baryons, must stay constant. Normally, matter isn't created or destroyed wholesale, it just rearranges. But in the extreme heat of the early cosmos, hypothetical processes might have temporarily bent this law, allowing a net surplus of matter to emerge. The final piece of the puzzle is out of equilibrium conditions. Picture a boiling pot left unattended. As steam escapes, the system shifts irreversibly, never returning to its original state. Similarly, the infant universe needed a moment of cosmic imbalance, a departure from thermal equilibrium, to lock in matter's advantage before annihilation could erase it. This might have happened during phase transitions, like when the primordial plasma cooled enough for forces like electromagnetism and the strong nuclear force to freeze out as distinct entities. These shifts could have created pockets where matter briefly dominated, like eddies in a river breaking the flow's symmetry. What's striking is how finely tuned these conditions had to be. Too much CP violation, and the universe might have ended up with far more matter, collapsing early under its own weight. Too little, and nothing would have survived annihilation. It's as if the cosmos threaded a needle, balancing Sakharov's conditions just right to leave behind the precise amount of matter needed for galaxies and life to form. The hunt for proof drives modern physics. Laboratories like CERN simulate these primordial conditions, smashing particles together to spot rare instances of baryon number violation. Meanwhile, neutrino experiments search for new sources of CP violation beyond what kaons revealed. Some theories even suggest undiscovered particles, like leptoquarks or heavy neutral leptons, could have mediated these processes in the early universe. Baryogenesis isn't just a theoretical curiosity, it's our origin story. Every atom in your body exists because, against all odds, nature's perfect symmetry fractured in just the right way. The mystery isn't fully solved, but each clue brings us closer to answering the ultimate question. Why is there something instead of nothing? Among all the particles that might hold the key to the matter-antimatter mystery, neutrinos stand out as the universe's ultimate ghosts, elusive, nearly massless, and capable of slipping through entire planets without a trace. But these cosmic phantoms could be hiding a deep secret. They might be their own antiparticles, a property so bizarre it could rewrite our understanding of symmetry itself. If true, it would mean that every neutrino is simultaneously matter and antimatter, blurring the line between the two in a way no other particle does. This idea, proposed by physicist Eta Majorana in the 1930s, suggests neutrinos could exist in a quantum state where distinguishing between particle and antiparticle becomes meaningless. Neutrinos already defy expectations by oscillating, changing flavors between electron, muon, and tau types as they travel. This chameleon-like behavior implies they have mass, something the standard model of physics originally didn't account for. But here's where it gets even stranger. Oscillations could also amplify CP violation. Imagine a neutrino starting its journey as an electron neutrino, then shifting into a muon neutrino, while its antimatter counterpart takes a slightly different path. Even a minuscule difference in how these oscillations play out for matter versus antimatter could have tipped the scales in the early universe, creating just enough surplus matter to build galaxies. Experiments like Japan's T2K and the Deep Underground Neutrino Experiment (DUNE) in the United States are racing to measure these subtle asymmetries. By firing beams of neutrinos and antineutrinos through hundreds of miles of Earth and comparing their oscillation patterns, scientists hunt for discrepancies that might reveal new sources of CP violation. The stakes couldn't be higher. If neutrinos violate CP more strongly than quarks, the particles involved in the kaon experiments, they could finally explain the universe's matter dominance. Yet the Majorana hypothesis takes this a step further. If neutrinos are their own antiparticles, they could have triggered a process called leptogenesis in the early cosmos. Here's how it might work. Heavy, as yet undiscovered neutrinos could have decayed asymmetrically, producing more matter than antimatter. This imbalance might then have cascaded into the baryon asymmetry we see today through interactions that converted leptons like neutrinos into baryons like protons. It's a cosmic Rube Goldberg machine, where one tiny asymmetry snowballs into the foundation of everything. The hunt for Majorana neutrinos involves some of the most delicate experiments in physics, like searching for a rare nuclear process called neutrinoless double beta decay. If observed, it would prove neutrinos are their own antiparticles by catching them vanishing into pure energy without releasing antineutrinos, a smoking gun for their Majorana nature. Teams like the Jurda and Legend collaborations are buried deep underground, shielded from cosmic noise, waiting for this telltale signal. What's mesmerizing is how these whisper-thin particles, so insubstantial they barely interact with anything, might have shaped the entire cosmos. Their oscillations, their potential self-annihilating nature, their hidden asymmetries, all could be fragments of a puzzle we're only starting to assemble. If neutrinos hold the answer, it would mean the universe's greatest imbalance hinges on particles that are, in every other way, practically invisible. The irony is delicious. The reason we exist at all might come down to the universe's quietest, most ghostly inhabitants. Deep beneath the French-Swiss border, inside a labyrinth of tunnels and detectors, physicists are performing what might be the most delicate balancing act in science, holding antimatter captive. At CERN Alpha experiment, researchers don't just observe antimatter, they trap it in magnetic bottles, suspending it in near-perfect isolation to study its properties atom by atom. Picture trying to cage lightning antihydrogen, the simplest antimatter atom, lasts mere seconds before annihilating if it so much as brushes the walls of its container. Yet Alpha team has stretched that time to minutes, even hours, by cooling antihydrogen to near absolute zero and using precisely engineered magnetic fields to levitate it in a vacuum. Their goal, to compare antihydrogen's behavior to ordinary hydrogen with unprecedented precision. According to the standard model, both should absorb and emit light at identical wavelengths. But if even a minuscule discrepancy appears, say, antihydrogen's spectral lines are slightly shifted, it could reveal cracks in the symmetry that might explain the universe's matter bias. In 2016, Alpha made history by measuring antihydrogen's light spectrum for the first time. The initial results showed no deviation, but the hunt isn't over. Future upgrades aim to refine these measurements 100-fold, searching for anomalies hidden in the decimal places. Meanwhile, just down the hall at the base experiment, scientists tackle an even more fundamental question. Do protons and antiprotons weigh exactly the same? Using a device called a penning trap, they've compared the charge-to-mass ratios of these particles with mind-bending precision, down to 1 part in a trillion. That's like weighing two identical-looking coins to detect a difference less than the mass of a single grain of salt. So far, antiprotons obey the rules, matching protons within experimental error. But BASE keeps pushing the limits, because if antiprotons turned out to be even slightly heavier or lighter, it would upend our understanding of why matter dominates. What's astonishing isn't just the precision of these experiments, but their audacity. BASE measurements are so sensitive they can detect the faint gravitational pull of a researcher walking past the apparatus. To cancel out Earth's magnetic field, the team uses superconducting shields cooled to temperatures colder than outer space. Every cable, every sensor is engineered to eliminate interference that could skew results by a trillionth of a percent. This isn't just science, it's a high-stakes treasure hunt where the prize is a flaw in the universe's blueprint, and the implications go far beyond antimatter. If alpha or BASE found even a hint of asymmetry, it could point to new forces or particles beyond the standard model, ones that might have shaped the cosmos in its first microseconds. These experiments are time machines in a way, recreating conditions so pristine they hint at the universe's infancy, when the fate of all matter hung on quantum uncertainties we're only beginning to measure. Every trapped antihydrogen atom, every precisely weighed antiproton, is a whisper from the Big Bang itself, asking us why anything survived annihilation at all. The math just doesn't add up. We've found CP violation, that tiny imperfection in nature's mirror, but its effects are like a single grain of sand trying to tip an entire scale. The known cases of asymmetry, like those in kaon decays, contribute just a fraction of what's needed to explain why the universe is swimming in matter while antimatter vanished into the void. It's as if we've uncovered one piece of a 1,000-piece puzzle, and the rest is still hidden in the box. So what's missing? This gap between theory and reality is the heart of the matter-antimatter asymmetry problem, and it's forced physicists to confront some unsettling possibilities. First, there's the question of whether we've underestimated CP violation's role. Could there be undiscovered particles or interactions where the symmetry breaking is far stronger? Imagine discovering a hidden lever in nature's machinery that, when pulled, creates a much larger imbalance. Some theories suggest heavy neutrinos or exotic particles predicted by supersymmetry might be the culprit, interacting in ways we haven't yet observed. Others speculate that CP violation might have been amplified in the extreme conditions of the early universe, conditions so alien that even our most powerful particle colliders can't fully recreate them. Then there's the puzzle of baryon number violation. Sakharov's framework demands it, but we've never directly observed protons or neutrons spontaneously transforming into pure energy. If baryon violation occurs, it must be incredibly rare, or require energies so high they've been inaccessible since the universe's first trillionth of a second. Experiments like those searching for proton decay in underground tanks filled with ultra-pure water are hunting for hints, waiting decades just to catch a single proton vanishing. So far, the proton's lifetime appears staggeringly long, leaving us to wonder, did baryon violation happen only in those fleeting moments after the Big Bang, or are we just not looking in the right way? Perhaps the most tantalizing unknown is whether antimatter hides in plain sight. Could entire regions of the cosmos be made of antistars and antigalaxies, separated from us by vast voids where annihilation fronts have cleared the boundary between matter and antimatter domains? If so, why haven't we detected the telltale gamma-ray flashes from collisions at these cosmic borders? Or worse, what if antimatter is fundamentally unstable over cosmic timescales, decaying into something we don't yet recognize? These aren't just wild guesses, they're testable hypotheses that keep telescopes and particle detectors humming with activity. And lurking beneath it all is the unsettling possibility that our understanding of symmetry itself is incomplete. What if CP violation isn't the only player? Could there be other, subtler asymmetries like differences in how matter and antimatter respond to gravity, or hidden quantum entanglements that favored one over the other. Experiments like CERN Alpha G are now testing whether antimatter falls up instead of down, a notion that sounds absurd but would rewrite physics if true. Every assumption is under scrutiny because in the end, the universe has already handed us its verdict, matter won. The challenge is figuring out how it cheated. This isn't just academic curiosity. Solving the asymmetry problem could reveal new forces, particles, or even dimensions physics beyond the standard model. It's a reminder that the cosmos isn't just stranger than we imagine, it's stranger than we can imagine. And until we uncover the missing pieces, the question remains, what broke the universe's perfect symmetry, and why did it leave us behind as the lucky leftovers? Among the most tantalizing ideas in modern physics is supersymmetry, a theory that suggests every known particle has a hidden, heavier twin we've yet to discover. These hypothetical superpartners could solve some of the universe's deepest puzzles, including the matter-antimatter imbalance. Here's how it might work. If supersymmetric particles exist, their interactions could introduce new sources of CP violation, far stronger than what we've observed in ordinary particles. Picture a seesaw with a tiny weight on one side, what we've seen with kaons, versus a massive counterweight suddenly dropping onto the other end. That's the kind of game-changing asymmetry supersymmetry might offer. Take the neutralino, a theoretical supersymmetric particle that could be its own antiparticle. If neutralinos existed in the early universe, they might have decayed unevenly, producing more matter than antimatter. Unlike the subtle effects we see today, these decays could have been wildly lopsided, skewing the cosmic ledger enough to leave behind the surplus matter we're made of. It's a compelling idea, but there's a catch. We haven't found a single supersymmetric particle yet. That's where next-generation colliders like the Future Circular Collider (FCC) come in. Designed to smash particles at energies 7 times higher than the Large Hadron Collider, the FCC could finally uncover these elusive superpartners. Imagine sifting through the debris of collisions at temperatures not seen since the universe's first trillionth of a second, conditions where supersymmetry might finally reveal itself. Detecting even one supersymmetric particle would open the floodgates, offering new ways to test whether these particles could have tipped the matter-antimatter balance. Yet supersymmetry isn't the only contender. Some theories propose that the real asymmetry boost came from particles we've already discovered, like neutrinos, but behaving in ways we don't yet understand. Others suggest entirely new forces that acted briefly in the early cosmos, leaving no trace except the matter-dominated universe we see today. The beauty of the hunt is that every dead end still teaches us something. If supersymmetry remains hidden, it might mean nature found another, even stranger way to break the rules. What's electrifying is how high the stakes are. Discovering supersymmetry wouldn't just explain the matter-antimatter imbalance, it could unite quantum mechanics and gravity, solve the mystery of dark matter, and rewrite textbooks overnight. But until we find proof, these elegant ideas remain cosmic maybes, floating just beyond the edge of our detectors. The FCC and other experiments are our best shot at pulling them into the light, answering the question that's haunted physics for decades. How did the universe cheat its own symmetry, and what else is hiding in the shadows? Imagine a universe where the tiniest, most ghostly particles hold the key to our very existence. That's the heart of leptogenesis, a theory where neutrinos, those nearly massless cosmic phantoms, might have triggered the matter-antimatter imbalance in ways we're only beginning to unravel. Unlike traditional baryogenesis, which focuses on quarks and protons, leptogenesis flips the script, suggesting that the real action happened in the neutrino sector. Here's the wild part. It all hinges on an elegant cosmic trick called the seesaw mechanism, where ultra-heavy neutrinos, ones we've never detected, could have decayed asymmetrically, tipping the scales in matter's favor. Picture a seesaw on a playground. On one end, you have the featherweight neutrinos we know, so light they barely register on the scale of subatomic particles. On the other end, they're hypothetical heavyweight cousins with masses billions of times greater. According to the seesaw mechanism, these gargantuan neutrinos wouldn't just be curiosities. They'd be relics from the universe's first moments, born in the searing heat of the Big Bang. As they decayed, they might have produced slightly more leptons particles like electrons and neutrinos than antileptons. That tiny bias could have then cascaded through the cosmos, transforming into the baryon asymmetry we see today. The brilliance of leptogenesis is how it connects two cosmic puzzles, neutrino masses and the matter-antimatter imbalance. For decades, neutrinos baffled physicists because they refused to fit neatly into the standard model. They shouldn't have mass at all, yet experiments proved they do. The seesaw mechanism elegantly explains this by tying their minuscule masses to the existence of those undiscovered heavy neutrinos. But here's the kicker. Those same heavy neutrinos could have been CP violators on a grand scale, decaying more often into matter than antimatter. Unlike the feeble CP violation we've observed in quarks, these decays might have been wildly lopsided, skewing the early universe just enough to leave behind the matter we're made of. How does this asymmetry transfer from leptons to baryons? Enter the Sphaleron process, a hypothetical phenomenon where quantum fluctuations in the early universe's soup of particles could convert lepton excess into baryon excess. It's like exchanging currency at the dawn of time. Leptons trade their asymmetry for baryons, leaving us with the protons and neutrons that built galaxies. The math is stunningly precise. For every billion antiquarks annihilated, a handful of surviving quarks would owe their existence to this neutrino-driven chain reaction. Yet leptogenesis isn't without its mysteries. Those heavy neutrinos remain theoretical, lurking beyond the reach of current colliders. Experiments like the proposed Future Circular Collider or upgrades to neutrino observatories could change that, hunting for indirect evidence in neutrino oscillations or rare particle decays. Even more tantalizing is the possibility that neutrinos are Majorana particles, entities that are their own antiparticles. If confirmed, it would mean neutrinos can annihilate themselves without a trace, a property that could have turbocharged leptogenesis in the universe's infancy. What's striking is how this theory turns conventional wisdom on its head. Instead of brute force symmetry breaking, leptogenesis suggests the universe's imbalance emerged from subtle, almost ghostly processes, neutrinos whispering asymmetries into the fabric of reality. It's a reminder that the answers to cosmology's biggest questions might not lie in the loud, violent collisions of particles, but in the quiet, almost imperceptible quirks of nature's most elusive inhabitants. And if leptogenesis is right, every atom in your body might ultimately owe its existence to particles so faint they can pass through light years of lead without a single interaction. Trapping antimatter is like trying to bottle lightning, only harder. The moment it touches ordinary matter, it vanishes in a flash of energy, leaving scientists with nothing but gamma rays and frustration. This is why the world's most advanced physics labs have spent decades perfecting magnetic traps so precise they could suspend a single antihydrogen atom in near-perfect isolation. Picture a cage made of invisible forces where antimatter floats in utter darkness, shielded from every stray atom, every whisper of heat, every magnetic hiccup that could doom it to annihilation. Even a single photon bumping into an antiproton could end the experiment. The numbers tell the story. Since the first antihydrogen was produced in 1995, we've created barely enough antimatter to cover a grain of sand, just nanograms after 30 years of effort. Compare that to the tons of ordinary matter we handle daily, and the scale of the challenge snaps into focus. Why so little? Start with production. Making antimatter demands particle accelerators like CERN antiproton decelerator, which smashes protons into targets to spawn antiprotons. But for every million collisions, maybe one antiproton survives long enough to be captured. Then comes cooling. These antiprotons are born screaming hot, moving near light speed. To tame them, physicists use techniques like stochastic cooling, where magnetic kicks gradually bleed off energy until the particles are slow enough to trap. It's like trying to catch bullets with oven mitts, then convincing them to take a nap. Storage is even trickier. Antimatter can't touch physical walls, so labs use penning traps, devices that combine magnetic and electric fields to levitate charged particles in a vacuum 100 trillion times emptier than space. Even then, the slightest fluctuation can ruin everything. In 2011, CERN Alpha team held antihydrogen for 16 minutes, a record that felt like a miracle. But here's the kicker: all that work yielded maybe a few hundred atoms at a time. Scale that up to a gram, and you'd need more energy than humanity currently produces in a year. Then there's the cost. Producing a single milligram of antimatter would cost roughly $100 trillion at current rates, enough to bankrupt nations. Even storing it demands cryogenic systems colder than interstellar space and magnets so precise they can compensate for Earth's wobble. One engineer joked that keeping antimatter stable is like balancing a pencil on its tip during an earthquake while blindfolded. Yet these aren't just engineering puzzles, they're cosmic ones. Every failed trap, every premature annihilation reminds us how perfectly balanced yet brutally unforgiving the universe's rules are. Antimatter doesn't just annihilate, it demands perfection, and in that demand lies a clue. If antimatter is so ruthlessly symmetrical, how did the universe ever tip the scales? The very difficulty of storing it hints at the fragility of the imbalance that allowed our existence. Maybe the cosmos didn't cheat, maybe it just found a crack in the mirror we're still learning to see. Antimatter rockets sound like the ultimate sci-fi dream, a propulsion system so powerful it could slash travel time to Mars from months to weeks, or even reach nearby stars within a human lifetime. The idea isn't just fantasy. NASA Advanced Concepts Institute has sketched designs for antimatter-driven spacecraft, complete with magnetic nozzles to channel annihilation energy into thrust. But behind the awe-inspiring blueprints lies a brutal reality of physics and economics that makes these engines a paradox. They're simultaneously the most efficient and most impractical propulsion system ever conceived. Let's break down the numbers. When matter and antimatter annihilate, they convert 100% of their mass into energy, far surpassing nuclear fission's measly 0.1% efficiency. Just 1 gram of antimatter reacting with 1 gram of matter releases roughly 43 kilotons of TNT worth of energy, enough to power a city for days. For space travel, that translates to mind-bending specific impulse, a measure of propulsion efficiency. While chemical rockets max out around 450 seconds and ion thrusters reach 10,000, an antimatter engine could theoretically hit 1 million. That's the difference between a rowboat and a hydrofoil, yet the hurdles are just as staggering. First, there's production. Creating even a microgram of antimatter, enough for a modest interstellar probe, would consume more energy than the entire state of New York uses in a year. Current facilities like CERN produce nanograms annually at costs exceeding $60 million per milligram. Then comes storage. Keeping antimatter from touching ordinary matter requires magnetic or electric traps so precise they'd make a Swiss watch look crude. Even the tiniest field fluctuation, say, from cosmic radiation, could trigger catastrophic annihilation. Imagine balancing a spinning basketball on a needle while riding a roller coaster. That's roughly the stability required. NASA designs acknowledge these limits with creative workarounds. One concept, the antimatter catalyzed microfission engine, uses trace antimatter to trigger tiny nuclear reactions, reducing fuel needs while sidestepping total containment nightmares. Another proposes solid antihydrogen pellets, antimatter frozen into inert chunks with inert gases, though no one's yet figured out how to manufacture them without, well, exploding. These aren't engines you'd fuel up at a spaceport. They're more like controlled bombs with thrust nozzles. The cost calculus is even more sobering. Sending a crude antimatter ship to Proxima Centauri might require 40 grams of fuel, a stash worth over $2 quadrillion at current production rates. That's global GDP's worth of investment for a one-way ticket. Even scaled-down robotic missions face energy budgets larger than some nations. It's like designing a car that runs on diamond exhaust, technically possible but bankruptingly absurd. So why keep chasing the dream? Because the alternatives generation ships, cryogenic sleep, or sublight probes taking millennia are equally fraught. Antimatter remains the only known physics-compliant path to relativistic travel without resorting to warp drives or other speculative tech. And while today's production methods are Stone Age-level crude, breakthroughs in laser-driven antimatter synthesis or quantum trapping could one day tip the scales. The irony is delicious. The same annihilation that makes antimatter rockets so potent also makes them nearly impossible to tame. Yet buried in those paradoxes might lie the key to our interstellar future, if we can ever learn to bottle the universe's most volatile fuel without blowing ourselves to stardust first. Gravity doesn't play favorites, or does it? That's the question driving CERN Alpha-G experiment, where scientists are testing one of the most fundamental assumptions in physics. Does antimatter fall down like ordinary matter, or could it defy gravity and fall up? Imagine dropping a feather and a lead weight in a vacuum. They hit the ground simultaneously because gravity accelerates all objects equally, regardless of mass. But what if the feather was made of antihydrogen? The answer could shatter our understanding of the universe. At the heart of Alpha-G is a vertical vacuum chamber, meticulously designed to measure the gravitational pull on antimatter atoms. The team crafts antihydrogen by merging antiprotons with positrons, then traps these fragile atoms in a magnetic bottle. But here's the twist: the magnets aren't just for containment, they are part of a precision balancing act. By gradually weakening the magnetic field at the top and bottom of the trap, researchers can let gravity take over, observing whether the antihydrogen drifts downward, upward, or does something entirely unexpected. The setup is so sensitive it can detect movements as tiny as 1/1,000,000th of Earth's gravitational pull. Why does this matter? If antimatter falls up, it would violate Einstein's equivalence principle, the cornerstone of general relativity that insists gravity treats all matter and antimatter the same. Such a discovery would demand a complete rewrite of modern physics, hinting at forces or symmetries we've never imagined. Even a slight difference in how antimatter responds to gravity could explain why the cosmos favored matter after the Big Bang. Picture a universe where antimatter literally floated away in those early moments, leaving matter behind to build galaxies. The first results, published in 2023, delivered a plot twist. Antihydrogen appears to fall downward like normal matter, at least within the experiment's current precision. But the story isn't over. Alpha-G's measurements still have a margin of error larger than the potential signal. Future upgrades aim to sharpen the data 100-fold, hunting for deviations hidden in the noise. And there's another tantalizing possibility. What if antimatter's gravitational behavior changes under extreme conditions, like near a black hole? This isn't just academic curiosity. If antimatter defies gravity, even fractionally, it could unlock technologies straight out of science fiction. Think anti-gravity propulsion or new energy sources. More profoundly, it would mean the universe harbors a bias deeper than charge or quantum spin, a gravitational asymmetry woven into the fabric of space-time itself. For now, the verdict is still suspended midair, much like those trapped antihydrogen atoms, waiting for the next experiment to tip the scales. While antimatter might seem like the stuff of sci-fi weaponry and star drives, its most life-changing application today happens in hospitals, not Hollywood blockbusters. Every day, doctors rely on the quiet annihilation of antimatter to save lives through PT scans, positron emission tomography. Here's how it works. Patients are injected with a radioactive tracer, often a sugar molecule tagged with a short-lived isotope like fluorine-18. As this isotope decays, it spits out positrons, the antimatter twins of electrons. Each positron instantly meets an electron in the patient's body, annihilating in a burst of gamma rays that detectors circling the patient pick up. These collision points map out metabolic hotspots with eerie precision, lighting up tumors like cosmic fireflies against the darkness of healthy tissue. What makes this technology revolutionary isn't just the antimatter fireworks, it's the biological intelligence behind them. Cancer cells, with their ravenous appetites, gobble up the tagged sugar faster than normal cells, concentrating the positron emissions exactly where they shouldn't be. A skilled radiologist can spot malignancies as small as a grain of rice, sometimes years before they'd show up on traditional scans. Modern PT machines fuse these antimatter signatures with CT or MRI images, creating 3D roadmaps that guide surgeons to tumors with GPS-like accuracy. It's a marriage of quantum physics and medicine so seamless that patients rarely realize their diagnosis depends on particles that, elsewhere in the universe, annihilate whole stars. The contrast with antimatter's pop culture reputation couldn't be sharper. Unlike Dan Brown's fictional Vatican-threatening vials or Star Trek's warp cores, medical antimatter isn't stored in glowing containers or weaponized. Those radioactive tracers, they're produced in hospital cyclotrons no bigger than a minivan, with doses so minuscule that the actual antimatter involved would barely cover a pinhead. The annihilation events happen inside your body, trillions of them, yet the total mass converted to energy is less than a single snowflake's worth. This precision engineering turns one of nature's most violent processes into a medical scalpel, revealing disease without destroying healthy tissue. Yet the mythology persists, fueled by misconceptions about scale. Yes, a gram of antimatter could level a city, but producing that gram would take CERN facilities millions of years at current rates. Meanwhile, the few nanograms needed for a PT scan cost less than many standard blood tests. The real magic lies in how physics harnesses these vanishingly small quantities. Each positron in your body travels barely a millimeter before meeting its electron match, creating gamma rays of such specific energy that scanners filter out all other noise. It's not about brute force, it's about reading the universe's most delicate signatures. The next frontier pushes this precision even further. Experimental tracer cocktails now target Alzheimer's plaques, Parkinson's proteins, and even immune cell activity, turning antimatter into a universal biological spy. Researchers are engineering isotopes with half-lives measured in minutes to reduce radiation exposure, while AI-enhanced detectors tease out fainter signals than ever before. One experimental technique called proton therapy even uses controlled antimatter production inside tumors themselves to obliterate cancer cells with sub-millimeter precision, a far cry from the indiscriminate explosions of movie lore. What's often overlooked is how these medical breakthroughs feed back into fundamental physics. Every PT scan is, in essence, a miniature antimatter experiment, offering real-world data on how positrons behave in complex environments. Hospitals have essentially become antimatter laboratories, generating more annihilation events in a day than all particle colliders combined. That synergy between quantum physics and oncology hints at a future where understanding antimatter's quirks might unlock not just starships, but cures for diseases we can't yet imagine. The universe's most elusive substance, it turns out, has already found its highest calling, not destruction but healing. Rising from the heart of our galaxy like ghostly titans, two colossal orbs of gamma rays stretch 50,000 light-years into space, one north, one south of the Milky Way's disk. These are the Fermi bubbles, first spotted in 2010 by NASA, a Fermi gamma-ray space telescope, and they're leaking antimatter like cosmic sieves. Within these gargantuan structures, positrons' antimatter electrons crash into their matter counterparts at energies that dwarf anything we can produce on Earth, lighting up the gamma-ray sky with whispers of annihilation. The sheer scale is staggering. If you could see them with the naked eye, each bubble would span half the night sky, dwarfing even the full moon. What carved these antimatter behemoths? One leading theory points to our galaxy's supermassive black hole, Sagittarius A, which may have gone through a violent feeding frenzy 6 million years ago. As it devoured stars and gas, it could have belched out jets of plasma at near light speed, inflating these bubbles like cosmic balloons. The antimatter positrons inside might simply be byproducts of high-energy collisions within these jets, ordinary astrophysics cranked up to 11. But there's a wrinkle. Some measurements suggest the bubble's gamma-ray signature doesn't quite match what such jets should produce. The energy distribution is off, like finding a fingerprint that doesn't match any known suspect. This anomaly has sparked wilder theories. Could the bubbles be evidence of dark matter annihilations? If dark matter particles collide and decay within the bubbles, they might spawn positrons as a byproduct. Or perhaps long-extinct stars made of antimatter anti-stars once dotted the galaxy, and their explosive death seeded these structures with antimatter debris. Even more radical is the idea that the bubbles are scars from a space-time-defying event, like a collision between our universe and an antimatter-dominated parallel cosmos. Each hypothesis dances on the edge of known physics, tempting scientists with the possibility of rewriting cosmic rulebooks. Yet for all their mystery, the Fermi bubbles aren't entirely unique. Similar structures, like the E-Rosetta bubbles detected in X-rays, hint that our galaxy's core might be a serial bubble blower, cycling through periods of violent activity. Andromeda, our galactic neighbor, shows faint echoes of comparable features. What makes the Fermi bubbles special is their antimatter payload, a glowing tracer dye revealing processes we can't see directly. Every gamma-ray photon from their edges is a clue, a puzzle piece in understanding how galaxies distribute energy and antimatter across cosmic time. The next generation of telescopes, like the Cherenkov Telescope Array, aims to dissect these bubbles with unprecedented precision. By mapping the antimatter's energy spectrum in finer detail, scientists hope to distinguish between mundane explanations and physics that might reshape our understanding of the universe. It's a reminder that sometimes the most profound discoveries aren't made in labs, but in the silent glow of structures so vast we barely noticed them until a decade ago. The Fermi bubbles may be ancient, millions of years old, but their secrets are only just beginning to surface. Perched atop the International Space Station like a cosmic bloodhound, the Alpha Magnetic Spectrometer, better known as MS-02, sniffs the void for traces of the universe's most elusive quarry, antihelium. This refrigerator-sized detector isn't searching for run-of-the-mill particles. It's hunting for fingerprints of antimatter domains that might still linger from the Big Bang. Imagine if whole regions of our galaxy or beyond were built from anti-stars and anti-planets, invisible to us except for the rare anti-atoms that escape their borders. AMS-02 could be the first to catch their scent. Since its installation in 2011, this 7.5-ton physics lab has analyzed over 200 billion cosmic rays with precision that would make Earth-bound detectors blush. Its magnets bend charged particles into curved paths, separating matter from antimatter like a cosmic fork in the road, while its silicon trackers map their trajectories with nanometer precision. But AMS-02 isn't just counting antiprotons or positrons, it's after something far rarer, antihelium nuclei. These would be smoking guns for primordial antimatter, since they're too heavy to form through random cosmic ray collisions. Spotting even a single antihelium nucleus would suggest entire antiworlds might be out there, annihilating at their edges and sprinkling us with exotic debris. The challenge: antihelium is cosmic needle in a haystack territory. For every 100 million helium nuclei AMS-02 detects, it might find one antihelium. The detector has to sift through a relentless barrage of cosmic rays, solar particles, and even false signals from collisions with space station hardware. It's like listening for a whisper at a rock concert while someone shakes your chair. Yet MS-02 keeps listening because the payoff would rewrite cosmology. If antihelium exists in nature beyond trace amounts, it could mean the universe's matter-antimatter separation wasn't total, that pockets of antimatter survived the Big Bang's annihilation frenzy like islands in a matter-dominated sea. What makes this hunt so electrifying are the tantalizing maybes. In 2017, MS-02 hinted at something odd in its data, a handful of events that could have been antihelium, though statistical noise left room for doubt. Subsequent analysis couldn't confirm them, but it couldn't rule them out either. That gray area is where physics gets thrilling. Maybe these signals were flukes, or maybe they were the first ripples of an anti-galaxy hidden in plain sight. Future upgrades and longer observation times could tilt the odds, but for now, MS-02 keeps gathering data, its sensors drinking in the cosmic wind as the ISS orbits Earth every 90 minutes. The implications stretch far beyond academic curiosity. If antihelium proves primordial, it would mean our universe is less uniform than we thought, a patchwork quilt of matter and antimatter regions separated by vast annihilation frontiers we've yet to detect. It would also raise new questions. How did these domains avoid wiping each other out? Are there antimatter equivalents of the Milky Way, their light indistinguishable from ours except for the telltale gamma ray glow at their borders? And if antimatter domains exist, could they host anti-life with anti-DNA and anti-consciousness? MS-02 can't answer those questions directly, but every antihelium candidate it spots is a breadcrumb leading us deeper into the cosmic unknown. While we wait for definitive proof, MS-02 data keeps challenging assumptions. Its measurements of antiprotons, for instance, show slight excesses that some theorists argue could hint at dark matter decays or even exotic antimatter processes. The detector has become a silent revolution in particle astrophysics, reshaping how we think about everything from cosmic rays to the fundamental symmetries of nature. Its endurance is a marvel too, despite being designed for a 3-year mission. Over a decade later, it's still collecting data with barely a hiccup, outlasting multiple space shuttle missions that serviced it. The search for antihelium embodies one of science's greatest gambles, investing years and millions into an instrument that might find nothing, or might stumble onto a discovery that redefines reality. Whether MS-02 ultimately confirms antimatter domains or rules them out, its data will force us to confront how little we truly understand about the universe's original asymmetry. Every orbit, every particle collision it records is a vote in the cosmic ballot box, one that might finally tell us if we're alone in the universe or if somewhere out there, our perfect opposites are staring back at their own detectors, wondering the same thing. At the shadowy intersection of antimatter's disappearance and dark matter's invisible grip on the cosmos lies one of physics' most tantalizing possibilities. What if the two mysteries are connected? Enter actions, hypothetical particles so lightweight they barely interact with ordinary matter, yet could be the hidden architects bridging these cosmic puzzles. Theorized in the 1970s to solve a quirk in quantum chromodynamics, actions have since emerged as leading dark matter candidates, but their potential doesn't stop there. These ghostly particles might also hold clues to why antimatter lost its cosmic duel against matter in the universe's first moments. Picture actions as cosmic diplomats, shuttling between the visible and invisible realms. In certain theoretical models, they could have influenced the early universe's phase transitions, those critical moments when fundamental forces separated and the cosmos cooled. If actions interacted ever so slightly differently with matter versus antimatter during these transitions, they might have tipped the scales, creating the tiny surplus of matter we see today. It's a delicate proposition. These particles would need to violate CP symmetry just enough to explain the imbalance, but not so much as to contradict precise particle physics measurements. The math is razor-thin, yet compelling enough that experiments like CERN CAST and the upcoming International Action Observatory are hunting for actions with detectors sensitive enough to hear their quantum whispers. The action's elegance lies in its dual role. As dark matter, it could explain why galaxies rotate faster than visible matter alone predicts their extra gravitational pull coming from vast halos of actions. As an antimatter mediator, it might explain why those early universe annihilations didn't cancel out perfectly. Some theories even suggest actions could have triggered leptogenesis by interacting with neutrinos, amplifying tiny asymmetries into the matter-dominated cosmos we inhabit. This isn't just theoretical sprawl, it's a calculated bet that nature reuses its quirks across multiple puzzles. Yet actions aren't the only players in this shadowy narrative. Other dark matter candidates, like weakly interacting massive particles WIMP, might also have antimatter linkages. Certain supersymmetric models propose WIMP that decay asymmetrically, favoring matter over antimatter. Or consider sterile neutrinos, another hypothetical particle that could have stirred the primordial plasma unevenly, leaving matter slightly more abundant. Each idea shares a common thread. The invisible 85% of the universe's mass might not just be a bystander to the matter-antimatter imbalance, but an active participant in creating it. The experimental hunt is as creative as the theories themselves. Deep underground, detectors like Xeno-NNT and LZ watch for dark matter particles bumping into xenon atoms. In space, telescopes scour gamma-ray data for anomalies that might signal dark matter decays. And in labs worldwide, scientists are crafting quantum devices chilled to near absolute zero, hoping to catch an action's faint signal as it morphs into a photon under strong magnetic fields. These aren't separate missions, they're different angles on the same grand question. How does the visible universe's fate intertwine with the invisible one? What's mesmerizing is how these theories reframe antimatter's disappearance. Rather than a fluke, it becomes a cosmic signature, a fingerprint left by processes involving both the matter we see and the dark matter we don't. If proven, it would mean the answer to why is there something rather than nothing might literally be hiding in the dark. Every galaxy's invisible halo, every undetected particle streaming through your body right now, could be part of a mechanism so subtle it shaped reality without leaving a trace until now. The universe, it seems, loves a good plot twist, and the antimatter-dark matter connection might be its most audacious yet. Antimatter's energy density is the stuff of legends. 1 gram packs the explosive punch of 43 kilotons of TNT, dwarfing the output of even the most powerful nuclear weapons. To put that in perspective, that tiny speck of antimatter could release roughly the same energy as the bomb dropped on Hiroshima, enough to power a city like New York for an entire day. The raw efficiency is staggering. Matter-antimatter annihilation converts 100% of mass into energy, a feat no chemical or nuclear reaction can match. It's the ultimate energy source distilled into its purest form. Yet the dream of harnessing this power slams headfirst into brutal realities. Producing just 1 gram of antimatter would require the combined energy output of every power plant on Earth running non-stop for years. Current facilities like CERN generate nanograms at costs that make platinum look cheap, $62.5 trillion per gram by some estimates. Storage is another nightmare. Antimatter can't touch container walls without annihilating, so it must be suspended in magnetic or electric traps with near-perfect precision. Even then, stray cosmic rays or microscopic fluctuations could trigger catastrophic failures. Imagine bottling a lightning bolt inside a house of cards. That's antimatter containment in a nutshell. The challenges don't end there. Scaling up production would demand particle accelerators the size of small countries, consuming more energy than they'd ever feasibly return. Unlike solar or nuclear, antimatter isn't a fuel source, it's a battery, requiring vastly more energy to create than it releases. The cosmic joke: we'd need antimatter-powered factories just to make antimatter efficiently, a paradox that keeps the technology light years beyond our grasp. But here's where the story twists. While antimatter energy remains a pipe dream, its theoretical implications are revolutionary. Studying annihilation teaches us about quantum symmetries, the early universe's conditions, and even potential propulsion for interstellar travel. NASA's hypothetical antimatter drives, though impractical today, rely on physics that could one day unlock relativistic speeds, and every trapped antihydrogen atom at CERN brings us closer to understanding why the cosmos favored matter, a puzzle whose answer might reshape physics itself. The irony is delicious. Antimatter's greatest value lies not in what it destroys, but in what it reveals. Those 43 kilotons per gram aren't just a measure of explosive potential. They're a beacon guiding us toward deeper truths about the universe's most fundamental imbalances. For now, it remains the ultimate cosmic tease, an energy source so perfect, so potent, that nature seems to have rigged the game to keep it just out of reach. Imagine the universe's first moments as the ultimate cosmic ledger, a balance sheet where matter and antimatter should have cancelled each other out to the very last particle. Yet somehow the math didn't add up, not by much, just the tiniest rounding error in the grand accounting of existence. For every billion antimatter particles annihilating with their matter counterparts, one single matter particle slipped through unscathed. 1 in a billion, that's the razor-thin margin that built everything, every star, every planet, every living thing. Zoom out to grasp how preposterously narrow this survival rate was. Picture two vast oceans of particles, one matter, one antimatter, colliding in the universe's first microseconds. The annihilation was so total, so complete, that space itself should have been left utterly empty. Yet somehow, amidst this all-consuming firestorm, a handful of matter particles avoided their doom. Scatter a billion grains of sand across a football field, then remove just one. That's the scale of imbalance we're talking about, except those surviving grains went on to construct entire galaxies. This lopsided budget raises a profound question. Why didn't the universe zero itself out? Physics insists on symmetry, yet here we are, the statistical fluke that defied annihilation. The numbers tell the story. Today's observable universe contains roughly 10 to the 80 particles. That means if the initial asymmetry was indeed 1 part in a billion, the early universe must have hosted 10 to the 89 particles before annihilation whittled them down. Wrap your mind around that number. It's more particles than there are atoms in 100 billion Milky Ways. All that chaos just to leave behind the scraps we're made of. What's astonishing isn't just the slim margin, but how perfectly calibrated it was. Had the imbalance been slightly smaller, say 1 in a trillion, the universe would have been too sparse for gravity to clump matter into stars. Slightly larger, and matter might have collapsed prematurely into black holes. It's as if the cosmos threaded a needle, landing on an asymmetry just precise enough to allow complexity to emerge. You can see echoes of this fragility in modern experiments. When physicists smash particles together at CERN, they recreate mini versions of that primordial annihilation, and the debris always shows near-perfect symmetry between matter and antimatter. The fact that we exist at all suggests some hidden mechanism tilted the scales when conditions were hotter, denser, and far stranger than anything we can replicate. This isn't just ancient history, it's written into your body right now. The atoms in your hands, your eyes, your brain are the direct descendants of that 1 in a billion surplus. Every breath you take is powered by starlight from matter that narrowly avoided annihilation 14 billion years ago. The universe gambled on an imperceptible asymmetry, and we're the living proof it paid off. Yet the ledger still doesn't balance. Until we find what caused that initial discrepancy, the universe's accounting remains a mystery, one where the tiniest rounding error made all the difference between nothingness and everything. The universe's first moments were anything but serene, a seething, frothing cauldron of energy where the very fabric of reality writhed with quantum uncertainty. Picture space itself boiling with particles and antiparticles blinking in and out of existence, their fleeting lives governed by the chaos of the Planck epoch. In this primordial frenzy, the scales of matter and antimatter teetered on a knife's edge, balanced by laws we're still struggling to decode. But quantum mechanics doesn't deal in perfect symmetry. It trades in probabilities and fluctuations, tiny imperfections that could have snowballed into the cosmic imbalance we see today. Consider the Heisenberg uncertainty principle, which allows particles to borrow energy briefly, creating spontaneous pairs of matter and antimatter. Normally, these pairs annihilate almost instantly, returning the energy to the vacuum. But in the extreme densities of the early universe, some of these fluctuations might have been frozen into reality before annihilation could occur. Imagine a vast ocean where bubbles form and pop relentlessly, except occasionally. A bubble escapes the surface, now scale that up to the entire cosmos, where escaping bubbles of matter could have tipped the balance. These quantum hiccups, amplified by the universe's explosive expansion, might have been the seeds of everything we know. The real intrigue lies in how these microscopic quirks could have scaled to cosmic proportions. Inflation, the universe's exponential growth spurt, would have stretched quantum fluctuations from subatomic to galactic sizes in fractions of a second. What started as random flickers in the quantum foam could have become the scaffolding for galaxies. But here's the twist: if matter and antimatter were truly identical, inflation should have smoothed out any asymmetry, leaving the universe perfectly empty. Instead, something broke the symmetry, and the leading suspect is a phenomenon called spontaneous symmetry breaking. Think of it like a pencil balanced perfectly on its tip. Theoretically, it's symmetrical, but the slightest perturbation, a quantum fluctuation, perhaps makes it tip in one direction. In the early universe, the tip might have been triggered by a phase transition, akin to how water suddenly crystallizes into ice. As the cosmos cooled, hypothetical fields like the Higgs or inflaton might have settled into uneven configurations, favoring matter production over antimatter. The catch: we've never observed a phase transition dramatic enough to explain the imbalance we see. Enter the multiverse hypothesis. If our universe is one bubble in a vast cosmic foam, each with different symmetries broken randomly, we might simply inhabit a rare bubble where matter eked out a victory. It's a dizzying thought that our existence hinges on a quantum roll of the dice in a reality where most outcomes led to total annihilation. The alternative. Physics beyond the standard model, where undiscovered particles or forces nudge the scales. Either way, the quantum fluctuations of the early universe weren't just noise. They were the universe's first and most consequential gamble. We think of stars as giant fusion reactors, fusing hydrogen into helium and bathing the cosmos in light. But what if some of those pinpricks in the night sky aren't made of matter at all? Enter the mind-bending possibility of anti-stars, stellar bodies composed entirely of antimatter, shining just like ordinary stars but with cores fusing antihydrogen into antihelium. At first glance, they'd be indistinguishable from their matter counterparts. Light doesn't care whether it's emitted by an electron dropping orbits in a hydrogen atom or a positron doing the same in antihydrogen. The photons are identical. Yet if anti-stars exist, their presence would rewrite cosmic history, hinting at pockets of the universe where antimatter avoided annihilation and clumped into celestial structures. The hunt for these phantom stars hinges on their one unavoidable giveaway: annihilation. Even in the vacuum of space, stray atoms of interstellar gas would occasionally collide with an anti-star's surface, triggering matter-antimatter explosions. These collisions would produce gamma rays with a very specific energy signature, 511 kiloelectronvolts. the telltale fingerprint of electron-positron annihilation. Telescopes like NASA's Fermi Gamma-Ray Space Telescope have scanned the skies for these signals, and in 2021, a team analyzing its data made a tantalizing claim. 14 gamma-ray sources in our galaxy couldn't easily be explained by known astrophysical objects. Could these be anti-stars? Skeptics point out that pulsars, black holes, and other energetic phenomena can also produce gamma rays near this energy. To confirm an anti-star, astronomers would need to rule out these mimics by checking for additional clues. Like an absence of neutrinos, anti-stars wouldn't emit them via normal fusion or an unusual ratio of gamma-ray to visible light output. Even then, the bigger puzzle is how anti-stars could form at all. The prevailing theory says matter and antimatter were thoroughly mixed in the early universe, making it nearly impossible for large antimatter structures to coalesce without being annihilated. If anti-stars exist, they'd imply regions where antimatter somehow avoided contact with matter long enough to collapse under gravity, a scenario requiring physics beyond our current models. The implications are staggering. A single anti-star would mean antimatter isn't just a lab curiosity or a fleeting byproduct of cosmic rays, but a fundamental building block of the cosmos. It could suggest the Big Bang's matter-antimatter separation wasn't uniform, leaving behind isolated antimatter galaxies. Or perhaps these objects are relics of a more exotic origin, like antimatter asteroids ejected from an antimatter-dominated universe beyond our observable horizon. The search continues, with next-generation telescopes poised to scan deeper and sharper, hunting for those faint, deadly glimmers in the dark. Whether they're out there or not, the quest itself forces us to confront how little we truly understand about the universe's original asymmetry, and whether we're alone in a cosmos that might still harbor its perfect opposites. Antimatter research is entering an era of precision so extreme it borders on the surreal. At the forefront is CERN ELENA, the extra-low-energy antiproton ring, a machine designed not to smash particles at unimaginable speeds but to slow them down to a crawl. Picture a high-speed train gently braking until its wheels barely turn. That's ELENA's mission with antiprotons. By decelerating these antimatter particles to just 1/10 their previous trap-friendly energies, ELENA delivers them to experiments like a concierge handing off a fragile package, minimizing the chaotic jostling that usually plagues antimatter studies. This isn't just about finesse, it's about unlocking antimatter's secrets at resolution so sharp, even the faintest deviations from matter's behavior can't hide. But ELENA is just the opening act. The proposed low-energy antimatter research LEAR facility promises to push the boundaries even further, combining antimatter cooling with laser spectroscopy so precise it could detect a single antiproton's heartbeat. Imagine measuring the infinitesimal wobble of an antihydrogen atom's electron, or rather its positron, with lasers so accurate they'd notice if it strayed by less than the width of an atomic nucleus over a distance equal to Earth's circumference. These experiments aren't just technical marvels, they're time machines recreating conditions so pristine they echo the universe's infancy, when the fate of matter and antimatter hung on quantum uncertainties thinner than a razor's edge. The stakes, if even a trillionth of a percent discrepancy emerges between how antihydrogen and hydrogen absorb light, it could reveal new forces or dimensions influencing antimatter differently. Some theories suggest antimatter might respond anomalously to gravity or dark matter, quirks masked until now by the noise of high-energy collisions. LEAR ultrasensitive traps could also test whether antiprotons decay faster than protons, a violation of the standard model that might explain why antimatter lost the cosmic war. Beyond CERN, projects like Japan's antiproton decelerator J-PARC and Germany's FLARE aim to democratize antimatter research, putting these exotic particles in the hands of more scientists. Meanwhile, quantum simulation breakthroughs hint at a future where antimatter's properties could be modeled without risking annihilation. a digital playground for testing wild theories before committing to billion-dollar hardware. The irony is delicious. To understand why our universe exists, we're engineering ever more elaborate ways to keep its shadowy twin from vanishing. Each trapped antihydrogen atom, each laser-cooled antiproton, is a defiance of cosmic oblivion, a whisper from the Big Bang itself, asking why anything survived at all. What's coming next could rewrite textbooks. Imagine antimatter clocks so precise they detect space-time curvature in a lab, or antimatter batteries storing energy at densities dwarfing nuclear reactors. The wildest ideas, using antimatter to probe the quantum vacuum structure or even test whether antimatter experiences time backward, a notion that sounds like pulp fiction until you recall physics' habit of turning absurdities into axioms. One thing's certain, as these experiments peel back layer after layer of antimatter's mysteries, they're not just chasing particles. They're hunting for the universe's original sin, the fleeting moment when symmetry broke and reality chose sides. And whether the answer lies in quantum foam, hidden dimensions, or something stranger still, the machines to find it are now being built, one precisely cooled antiproton at a time. What if our universe's matter-dominated reality is just one option on a cosmic menu, and somewhere out there, floating in the infinite expanse of the multiverse, entire realms made of antimatter thrive undisturbed? This isn't just wild speculation, it's a serious thread in modern cosmology, woven from the same theories that explain why our universe exists at all. Imagine the Big Bang not as a single event, but as a foaming sea of quantum bubbles, each inflating into its own universe with its own rules. In this vast cosmic froth, some bubbles might have wound up with physics identical to ours except with matter and antimatter perfectly flipped. The idea springs from inflationary theory, which suggests our universe underwent exponential expansion in its first moments. But inflation doesn't have to be a one-and-done deal. Quantum fluctuations could have spawned countless bubble universes, each with randomly determined properties. Just as coins tossed infinitely will eventually land on heads a billion times in a row, some of these bubbles would statistically end up dominated by antimatter. The kicker, we'd never know. These antimatter universes would be forever cut off from us by the relentless expansion of space, their light eternally beyond our cosmic horizon. Here's where it gets even stranger. If antimatter universes exist, they might not look any different from ours at first glance. Stars made of antiprotons and positrons would still fuse antihelium, releasing photons indistinguishable from starlight. Antiplanets could orbit antistars in anti-solar systems, with chemistry identical to ours just built on antimatter's inverted charges. Even life, in theory, could arise in these mirror realms, pondering why their universe favored antimatter while wondering if matter-dominated bubbles like ours were possible. But how could such bubbles avoid annihilation? The key lies in their isolation. During inflation, space expanded faster than light, preventing matter and antimatter domains from colliding. Picture two soap bubbles floating apart in a tub. Their surfaces never touch. Any regions where matter and antimatter did meet would have self-destructed in gamma-ray bursts, leaving behind only the lucky bubbles that happen to be purely one or the other. Our universe, then, isn't special, it's just one survivor in a cosmic game of Russian roulette where most chambers held annihilation. The multiverse hypothesis doesn't stop at antimatter. Some theories suggest these bubbles could have entirely different physical constants, dimensions, or even laws of logic. But antimatter domains are among the few alternate universes that wouldn't require rewriting physics, just flipping a quantum switch. Experiments like MS-02 hunting for stray antihelium nuclei are, in a way, searching for evidence of these phantom neighbors. A single detection could imply that somewhere beyond our observable horizon, an antimatter twin universe floats just out of reach. Yet the wildest twist isn't that antimatter universes might exist, it's that they could outnumber ours. If the initial conditions of the multiverse favored no particular symmetry, matter and antimatter bubbles should be equally likely. Statistically, we might be the outliers. This inversion of perspective forces a humbling thought. Our entire reality, from galaxies to glaciers, could be the cosmic exception rather than the rule. The multiverse idea remains untested, hovering at the edge of science and philosophy, but it reframes antimatter's mystery from "why did it vanish" to "did it vanish elsewhere too?" Maybe, just maybe, our universe isn't the one that cheated symmetry. We're simply living in the bubble where matter got lucky. Until we find a way to peek beyond the inflationary curtain, the antimatter multiverse remains a tantalizing what if, echoing through the equations of cosmology and the human imagination alike. We take for granted that the universe is built from matter, that stars shine with familiar fusion, that chemistry follows predictable rules, that life as we know it even exists. But this wasn't guaranteed. The fact that you're here to ponder these questions hinges on an absurdly narrow cosmic margin, that 1 in a billion surplus of matter surviving annihilation in the universe's first moments. Flip that ratio slightly, and consciousness might never have emerged anywhere, just an endless void dotted with the cooling ashes of perfect symmetry. This razor-thin imbalance forces a humbling perspective. Life isn't just lucky to exist within the universe's laws, it's lucky those laws permitted existence at all. Physics could have been entirely consistent yet sterile, its equations balanced to mathematical perfection with no leftover matter to build galaxies or minds. Instead, we inhabit a peculiar corner of possibility where the numbers lined up just right. Theologians debate divine purpose, physicists crunch probabilities. But both confront the same awe that against staggering odds, the universe chose structure over silence. Was this inevitable? Some theories suggest universes with different matter-antimatter splits constantly bubble into existence, most inhospitable to complexity. We simply occupy one where the numbers allowed stars and planets to form an anthropic selection bias. Others propose deeper laws mandating slight asymmetries, making life-bearing universes statistically likely. Then there's the radical notion that matter's dominance isn't universal, that beyond our cosmic horizon, antimatter domains flourish with equal right, their physicists equally baffled by their own survival. These possibilities ripple beyond astrophysics into philosophy. If antimatter's near absence was a quantum fluke, does that render existence absurdly fragile or astonishingly resilient? Every atom in your body is testament to chaos narrowly channeled into order, like a tornado passing through a junkyard and assembling a working clock. Yet here we are, that clock's gears turning, asking why it ticks. Perhaps most unsettling is the alternative, a multiverse where all outcomes play out, and we merely inhabit the timeline where matter won. In this view, our existential pondering is itself a product of the imbalance. No surplus, no philosophers. The universe doesn't favor life. Life exists where the universe permits it. This shifts the question from "why are we here?" to "what does our presence reveal about reality's deeper structure?" The mystery lingers like a shadow across disciplines. Biologists studying life's origins, chemists tracing molecular bonds, even artists capturing the night sky, all engage with matter's legacy. Every scientific measurement, from the spin of electrons to the redshift of galaxies, assumes matter's dominance as foundational. Yet that foundation rests on an unproven anomaly, a crack in cosmic symmetry we've yet to fully explain. This isn't just about particles, it's about the precondition for meaning itself. A perfectly symmetrical universe might be aesthetically pleasing to a physicist's equations, but it would also be sterile. No planets, no paintings, no proof that anyone was ever here to ask why. Matter's fragile victory, whatever its cause, granted the cosmos more than structure. It granted a story, and we are that story's latest sentence, still searching for the words that came before. Ever stumbled across a YouTube video claiming someone made antimatter in their garage with a microwave and some spare parts? The internet loves these wild DIY stories, from homemade fusion reactors to backyard particle accelerators. But when it comes to antimatter, the gap between viral fantasy and reality isn't just wide, it's cosmic. Let's cut through the hype. Creating even a single antihydrogen atom outside a facility like CERN isn't just difficult. It's practically impossible without millions of dollars in equipment, decades of expertise, and infrastructure that dwarfs most city blocks. First, the scale issue. To produce antimatter, you need particle accelerators capable of slamming protons into targets at nearly light speed, generating antiprotons as rare byproducts. CERN Antiproton Decelerator, a machine the size of a small apartment building, churns out about 15 million antiprotons per minute. Sounds impressive until you do the math. That's roughly 25 picograms trillionths of a gram per year. To collect enough for a visible speck, say 1 microgram, you'd need to run CERN's entire operation non-stop for 40,000 years. And that's just production. Storage, forget Tupperware. Antimatter demands vacuum chambers 100 trillion times emptier than space, coupled with magnetic traps precise enough to counteract Earth's own magnetic field fluctuations. Even a stray cosmic ray can ruin everything. Then there's the energy paradox. The laws of physics don't forbid making antimatter at home, they just make it hilariously impractical. The energy required to produce 1 gram of antimatter exceeds the annual output of multiple nuclear power plants. Even if you somehow cobbled together a garage-scale accelerator, which would likely electrocute you or irradiate your neighborhood, you'd need the power grid of a small nation to run it. And for what? A nanogram-sized explosion. The viral videos claiming breakthroughs usually misrepresent mundane physics like plasma balls or static electricity as antimatter. Real antimatter production leaves no room for ambiguity. It's either detected by billion-dollar spectrometers or it doesn't exist. Safety is another myth buster. Pop culture treats antimatter like a doomsday substance, but the actual risk from homemade attempts isn't annihilation, it's futility. The energies needed to create even a few antiprotons far exceed what's survivable in an unshielded environment. CERN teams wear dosimeters and operate behind layers of concrete and lead because the real danger isn't antimatter. It's the X-rays and gamma rays generated during production. A garage tinkerer wouldn't live long enough to see their first antiproton. What's revealing is how these myths persist despite the hard numbers. Antimatter captivates because it feels like the ultimate hack, nature's cheat code. But the reality is a testament to how finely tuned our universe is. The fact that antimatter is almost within reach, yet just beyond our grasp, mirrors the cosmic imbalance itself, a tantalizing near symmetry with a fracture we're still learning to measure. So next time you see a DIY antimatter headline, remember, the real marvel isn't what's possible in a garage. It's what's possible when humanity pools its knowledge across borders, decades, and disciplines to bottle the universe's most elusive substance, one painstaking atom at a time. If antimatter had won the cosmic war, our universe might look radically different, not just in composition, but in its very fate. While today's cosmos is dominated by dark energy's mysterious push, driving galaxies apart at an accelerating clip, antimatter's lingering echoes could have subtly altered this trajectory. Picture a universe where antimatter pockets survived annihilation. Their gravitational tug and annihilation fronts might have created chaotic density variations, warping spacetime in ways dark energy's smooth influence never could. Instead of a cold, sparse heat death, we might have faced a fractured cosmos littered with gamma-ray scars from colliding matter and antimatter domains. Yet in our reality, antimatter's impact on cosmic expansion is negligible, not because it lacks gravitational influence, but because so little remains. Even if every positron in the Milky Way suddenly vanished, the effect on galactic dynamics would be dwarfed by the gravitational pull of dark matter or the repulsive force of dark energy. The numbers are stark. All the antimatter produced in human history, if annihilated at once, would release less energy than a single supernova, a drop in the ocean of cosmic-scale forces. The real intrigue lies in hypothetical scenarios. If antimatter had formed stable structures like anti-stars or anti-galaxies, their gravitational dance with matter counterparts could have seeded exotic large-scale anomalies, voids where annihilation cleared space, or filaments glowing with residual radiation. Some models even suggest antimatter domains might warp spacetime differently due to CPT symmetry violations, potentially creating localized regions where expansion rates deviate from the norm. These ideas remain speculative, but they highlight how finely tuned our universe's imbalance had to be to avoid such turbulence. Contrast this with dark energy's role. While antimatter's potential influence fades as the universe expands, dark energy's grows, its repulsive effect scaling with space itself. The cosmic acceleration we observe today suggests dark energy's density remains constant even as the universe stretches, a property antimatter could never match. Annihilation events release energy, but they don't create the relentless pressure driving galaxies beyond each other's horizons. Still, antimatter's ghostly presence lingers in cosmic equations. The gamma-ray background carries whispers of ancient annihilation, and some theories propose that antimatter's initial asymmetry might have indirectly shaped dark energy's dominance. If early universe phase transitions favored matter's survival, they could also have triggered vacuum state changes that later fueled dark energy's rise. It's a tangled web of cause and effect where solving one mystery might unravel another. Ultimately, antimatter's role in the cosmos isn't about brute force influence. It's about the fragility of the conditions that allowed anything to exist at all. The universe's fate hinges on forces far more dominant, but those forces only matter because antimatter lost the battle 14 billion years ago. In a way, dark energy's lonely reign is the epilogue to antimatter's near-perfect annihilation, a cosmic silence bought by the narrowest of victories. From Dirac's scribbled equations predicting antimatter's existence to Anderson's accidental discovery in a cloud chamber, the hunt for cosmic asymmetry has unfolded like the greatest detective story in science. Each clue, from the slight wobble in kaon decays to the painstaking measurements of trapped antihydrogen, has rewritten our understanding of reality while deepening the mystery. Laboratories have become time machines, recreating conditions unseen since the universe's first microseconds, while telescopes scan the skies for antistars or the faintest whiff of antihelium. Yet the central question remains, why does anything exist at all? The irony is breathtaking. We've built machines precise enough to measure a single antiproton's weight to within a trillionth of a percent. Yet the answer to matter's survival might lie in effects too subtle for even these tools to detect. Or perhaps we're searching in the wrong places, missing some hidden asymmetry in neutrinos, dark matter, or even gravity itself. The very difficulty of the hunt mirrors the universe's original imbalance. Just as one extra matter particle in a billion slipped through annihilation, our discoveries often hinge on anomalies buried in vast datasets, statistical whispers hinting at cracks in the cosmic mirror. What makes this quest extraordinary isn't just the sophisticated technology, it's the human persistence behind it. Generations of physicists have chased shadows, from Dirac's reluctant acceptance of his own equations' implications to modern teams collaborating across continents to cool antimatter to near absolute zero. Every null result, every failed hypothesis has tightened the constraints on possible solutions, inching us closer to answers that might rewrite physics textbooks. The story isn't just about particles, it's about curiosity itself, the stubborn refusal to accept we don't know as a final answer. So where does the trail lead next? Maybe to the next CERN experiment spotting an unexpected wiggle in antihydrogen's spectral lines. perhaps to a neutrino detector catching evidence of Majorana particles, or a space telescope finally confirming an anti-star's gamma-ray signature. Or the breakthrough could come from somewhere entirely unexpected, a flash of insight from a graduate student's midnight calculations, an anomaly in a tabletop experiment no one thought to connect to cosmology. The beauty of science lies in these possibilities. Every unanswered question is an invitation, every unsolved mystery a challenge. The universe has shown its cards just enough to keep us guessing, 1 part symmetry, 1 part mystery, and a billion parts wonder. The next chapter in Antimatter's story isn't written yet, but the tools to uncover it are in our hands. All we have to do is keep looking.